Jeremy Renshaw, thanks so much for coming to the Titans of Nuclear studio to record today.
Thanks for having me.
So you had kind of a crazy trip here. Glad you made it in one piece.
Thank you. I'm running on 3 hours of sleep.
But you're going to do a great job anyways. It's what you do. So you're program manager of used fuel and high-level waste management at EPRI.
Yes, that's correct.
Cool. And what's EPRI?
EPRI is the Electric Power Research Institute.
And you guys are located in North Carolina? Or you specifically
Yes,
are?
I'm in North Carolina.
So it was quite a trip up for you here today, and probably a lot muggier and cittier than North Carolina.
It's pretty similar. It's a little bit warmer here today, and
Yeah.
I've been outside in the sun quite a bit more than in Charlotte, so
yeah,
I've been a little bit sweaty.
But that's okay. Because of electricity, we got
Keeps us
AC.
cool. Yep.
Yeah, we're nice and comfortable here. So you live in North Carolina, but where are you originally from, and how did you end up in North Carolina?
So I'm originally from Iowa, and I grew up there, went to school there, and when I was graduating, it was 2009, wonderful time. There were no jobs anywhere, but there were a couple jobs in Charlotte, so it was exactly what I wanted to do. It was in nondestructive evaluation, or NDE, so my wife and I made the trip. We loved it, and we've been there ever since.
So when you decided to stay in Iowa for school, was that because the university had the program that you wanted, or because you loved Iowa, or why did you stay?
Well, it was a little bit of my wife loved Iowa, and it was the program that I wanted to do. So those two lined up together.
So you were married before you went to school?
My wife and I got married during undergraduate, so.
Oh, nice. That's a lot for an undergraduate to handle. No?
Yeah.
The wedding planning as you're trying to graduate?
Yep. And then we had 2 kids before I finished graduate school, so we were all kinds of busy.
Yeah. And so your kids are in their teens now?
Yeah, my oldest daughter turns 13 this year.
Amazing. That's a tough age.
Oh, she's wonderful.
Yeah.
Super easy.
Any hints of her being interested in the nuclear industry?
I don't know about nuclear, but she is definitely an engineer.
Yeah.
She's on a robotics team. Actually, all my kids are on robotics teams now.
Look at that.
My daughter's team went to the World Championships in robotics last year and placed 6th place.
It's amazing.
So they did really well, yeah.
Congrats to her. What's her name?
Her name's Brooklyn.
Congrats, Brooklyn.
Yep.
Hopefully she'll listen to this and hear her shout out.
Yep.
And so you got married, you had kids, you graduated undergrad, you graduated grad school, all within the span of, 9 years?
Yeah, and I took 2 years off from school to go on a mission, so it was kind of like 7, but kind of like 9, depending on how you look at it.
Go on a mission? What was that for?
It was for my church. So I went down to Brazil for 2 years, learned Portuguese, met a bunch of wonderful people, and then came back.
That sounds amazing. So did you learn Portuguese before you went, or just as you were there?
They put us in a 2-month training camp and basically said, learn as much as you can, and off you go.
Yeah. Wow.
So it was a fast-paced learning environment.
Yeah. And what did you get to do in Brazil?
Oh, all kinds of things. So we talked with people, we did service, we taught English, we just helped in any way that we could.
Interesting. And so was it hard then to come back to a technical field after being for 2 years more working with people?
I had definitely lost a little bit, had to catch up. So yeah, definitely it took a lot to get back up to where I had been when I left.
Yeah. But I guess it was like it sounds like instinctually you and now your family have like this natural inclination towards engineering and learning.
Yeah, we like math, science, all that.
And is that because were your parents or your siblings interested in stuff?
Yeah, my older brother was a rocket scientist, so he worked for the United Space Alliance and was shooting off rockets and spaceships and all that. And then my younger brother, one of them works at NASA, one's getting a PhD in robotics, so we're all engineers.
Yeah, amazing. And then you had a girl. I'm glad you brought a girl into the family because it sounds like you guys were 3 brothers, which is a lot to handle.
Yeah, my family was 7 total, so 4 boys, 3 girls.
Wow.
Yeah, and my sisters are no slouches either. One has a PhD in traumatic brain injuries, so medical
Amazing.
PhD. The others are very smart. One is working, well, one's a stay-at-home, well, two of them are stay-at-home moms now, but they did work and they were very good at what they did. So it's kind of almost like a friendly competition between everyone. So they're all really
Who's
smart.
the smartest?
Oh, probably all of them, but we all have a lot of fun when we're together. So it's a great place to be.
Yeah, that's great. And one more prying into your family life question.
Mm-hmm.
Do you guys all live in North Carolina, or are you dispersed?
We're all over the place. So we have one in New York, two of us are in North Carolina, two are in Iowa, one is in Washington, and who am I missing? One is actually not too far from here in Maryland. They just moved from Chicago.
You should visit them.
I tried to. I haven't yet. They just moved here a few months ago.
They might have some clothes for you to borrow or things for you to use.
Since mine never showed up.
Yeah. No, but that sounds like an amazing upbringing, great foundation for getting into the field, and probably a big motivation of why you did grad school. So why did you do grad school, and what did you study in grad school?
Well, when I was getting near the end of school, I realized I either had to get a job or go to grad school or do something with my life rather than just graduate and be a bum. And I had taken a class in nondestructive evaluation, and it was, I don't know if it was just that I really loved the material or the professor was just amazing, but I think it was a lot of both. And so that professor was Bruce Thompson, and who's like this icon in the nondestructive evaluation world. And so he had taught this class, and so then I went on to be a grad student for him and for Steve Holland, who was kind of a protege, whiz kid professor. And so then I got to work with both of them for several years, and it was kind of like a confluence of destiny that everything just came together exactly how it felt like it should.
Yeah. And for our listeners who don't know, what is nondestructive evaluation?
So it's kind of like having a superpower where you look inside of materials and see what's there. So it's things like X-ray, ultrasound, eddy current, even visual can be an NDE technique. My specialty was thermography, so evaluating heat patterns and distribution of heat and heat flow to find defects.
Interesting. And why do we need all those different types of evaluation? Why can't we say just use X-ray for everything?
Well, that's a great question. And the reason is there are positives and negatives to every technique. So there's nothing that's a one-size-fits-all perfect match. So X-ray is very useful in many applications. Some areas it's weak. Same with ultrasound or any other technique. They have kind of their area where they're strong, but they have other areas where they're weak. So.
And in terms of like the thermal mapping, what areas was that the strongest for, and did that sort of lead you into the nuclear field because it's used for nuclear?
So what that was really useful for is what we were testing it on at the time was aircraft components. And one of the neat things about it is we were looking for cracks, and so what you do is we'd use a technique called vibrothermography. So you'd shake a part, that's where the vibro comes from, and thermography is you'd look at the heat. So you'd have things like crack faces that would rub together or delaminations or other defects. And so you'd see differential heating, even if it was for just a split second, at those locations. And so then you could map those to defects. And one of the interesting things was that in some cases you could find defects with this technique that nothing else could find. And in one case, and I can't talk much more than generalities because it was a certain aircraft manufacturer, they found a defect that nothing else would have found that would have cost millions of dollars of damage had it not been found, and potentially people could have lost their lives too.
Wow. So that sounds crazy to me that a heat crack that we may never have found if we hadn't used this imaging could have such a financial and like life-threatening impact. It's like, how do you know what you don't know? In a sense, how would you know that that's even important to look at and to study, to keep pushing the way that we do the testing?
Well, really, it comes down to understanding materials and their behavior. So we try and run materials, we have the best materials that we know of. We try and use them in the right applications. So when we have pipes, sometimes we need high temperature and corrosion resistance. When we have airplane components, they need to be able to withstand very high temperatures and sometimes have creep resistance or other things like that. So we tailor the materials to the application, but then each material, again, just like the NDE techniques, nothing is perfect. No material is perfect. In fact, all materials have flaws and defects of various sizes, whether it's on the size of the grains or even smaller. All materials have defects. And so what we try and do with the inspection techniques is identify those materials and find defects of a certain size that could cause failure.
Yeah, that's really interesting. It's such a specific field, which grad school is perfect for studying.
Yeah.
But what do you do after it, you know?
So after that, then I went to work for a nuclear vendor, kind of furthering some of that, as well as working on some ultrasonic techniques to inspect reactor internals. And from that, I got a call from EPRI several years later saying, hey, we want you to do the same thing, but instead of working for a vendor, you can do it for a nonprofit, for the greater good, for the general public benefit. And that really spoke to me of not trying to make money for a specific company, but really trying to make a difference in the world.
Interesting. You don't think that the two can go hand in hand?
Oh, they can. You can definitely make a living while making the world a better place, but it was kind of the change in vision and mission statement that really attracted me to EPRI.
Interesting. And so you said that when working at the vendor, you were using the the heat mapping techniques to look at which part of the plant was it?
Well, I can't say.
Oh, you can't say. Okay, so to look at components in the plant. And so in that sense, when you're talking about, doing that sort of analysis to help a company make a profit, it helps make them a profit in the sense that, okay, we found somewhere that the material is cracking or performing less than we'd hope it would, and then because of that, we're going to change the material? Or what's the outcome of determining those imperfections in terms of a business sense?
Yeah, so from the business side, the reason you do inspections is to prevent failures. So there's two acronyms of NDE. There's non-destructive evaluation and near-death experience. And I like to say proper NDE, non-destructive evaluation, prevents NDEs or near-death experiences. So you do NDE, you do your inspections to find materials or flaws. Now, most of the time, they're not going to cause death or destruction or anything, but you can have unplanned outages, you can have pipes that break, you can have bolts that break, you can have all kinds of things that fail and cause lots of headaches. So you inspect so that you know what to repair, replace, and potentially change the material or component or design. So typically the inspections are done to identify flaws, to take things out of service and be repaired or replaced.
And are these inspections required by regulators at certain time intervals, or is this something that the company just decides to do at certain time points?
In some cases, regulations will require time-based inspections. In some cases, they're done opportunistically. Hey, we're taking this pump apart, let's inspect the internal components. Or in other times, it's just the plant says, hey, we want information on this component. So they'll go and do inspections.
Interesting. And are you at will to use whatever type of inspection technique that you want? Or are there rules behind that as well?
Typically what they have are qualification programs. So as long as you can demonstrate that your technique will find the flaws of interest in the component you're inspecting, there's no real restriction that you have to. Well, in some cases there are, but typically there are no restrictions that say you have to use this technique. It's really, you have to find this flaw or meet this safety requirement. And then it's up to you how you meet the requirement.
And how do you prove that you're going to do something like that? Is that modeling?
A lot of times you do modeling. Other times you make mock-ups. So if you're inspecting a bolt, you make a bolt. If you're inspecting, let's say, a cup, you would make a cup that is as representative as you can, the same materials, the same geometry, the same size, and then you would inspect, and you would put in your mock-ups intentional flaws in certain orientations and locations that might be representative of what you find in the field. So if you have a bolt, you would put it typically in the bolt to shank radius because that's the highest stress region, or in some of the threads. So if you have a pipe, a lot of times in the weld region, either in or around the weld, especially in the heat affected zone, which is just outside of the weld. So those are the areas that are most susceptible. So those are the ones that are inspected.
Do you ever go the opposite way? So for your example, when you were looking at the part of the aircraft and you found a crack that you guys hadn't been able to detect before, then do you try to recreate that crack in like a test component and see if it picks it up again?
Yeah, so you'll put flaws in various locations, and one of the things that we had worked on, and this was way back in grad school, was artificial flaws. So where you could put something in and maybe not actually damage the material, but have some kind of marker or substance or substrate that you could attach on that would behave like a flaw, but not actually be a flaw. So then you could move them around. And one of the things that I'm not doing, but other people at Epri are doing, are working on virtual mock-ups, where you can take actual data from real flaws and put it into a model, and then you can scan around and find real flaws in a model or in a virtual mock-up. So
So
very
it's like,
interesting things going on over with those NDE guys.
Yeah. So it'd be like taking a flaw in one item and then taking that data and putting it into a program that already has like the base structure of another item that could or couldn't have these flaws, but you're seeing if it can or can't have the flaws by testing them in the model.
Yeah, we're looking at what's called probability of detection. So if you have a flaw, you want to be able to find it. Now, no ND technique would be perfect in any case. You know, you'll always miss some flaws, whether they're too small or too tight, or in a configuration where your energy just doesn't get there, whether it's X-ray, ultrasonic, whatever kind of energy you're using. And so you do these probability of detection curves to understand what size distribution can I find and how reliably can I find those flaws.
And how reliable is it usually?
Well, that is the question. So if you have larger flaws, half an inch or more, they're typically very easy to find. But when you get down to flaws that are a millimeter, half a millimeter, or smaller, those can be very difficult to find. Now, some techniques will do very well, and some less so.
And do you ever use multiple techniques on one part? Absolutely.
In fact, one of the big projects we're working on right now is inspecting dry storage canisters. They're these very large, 6 foot in diameter, 15 plus foot tall canisters that are exactly that. It looks almost like a large cup.
Yeah.
They have nuclear fuel inside, and we've been developing robotic systems to go in and inspect these canisters. And what you'll typically do first is look at them visually. So you go all around, this very large canister and inspect, and if you see anything that doesn't look perfect, if you see anything that's not bright, shiny metal, you would want to go look closer. And then you could go and use other techniques, things that are more sensitive, things like ultrasound, eddy current. We can even take sampling of these canisters. So there's a lot that goes into that.
And do the robots do that while they're there? Or do
Yes.
they extract the sample and then you guys do that back in the lab?
So this is really cool. So back when we started that project, everyone said, oh, these canisters are uninspectable. It's impossible. You'll never be able to do this. And so what we set out to do, because these canisters have very high radiation rates.
So this is this is spent fuel.
Yes, this is spent fuel.
Yeah.
So once it's been out of the reactor in the spent fuel pool and then loaded into what's called dry storage canisters. And it'll sit there for long periods of time, waiting to go to a repository, which
doesn't exist.
Doesn't exist
At
yet.
this
So
moment.
it's all dressed up, but nowhere to go. So it's sitting inside of a canister, and then the canister is inside of a concrete vault, typically for shielding. And so you'll have typically a 2 to 4 inch gap, or if we're talking, the metric system, 50 millimeters to 100 millimeters. And so we've developed 3D printed robots that can navigate into these tight, confined, high temperature, high radiation spaces, and then do these very difficult, complex examinations. but make it so it's not that hard and not very expensive to do.
And are they 3D printed because that is less expensive and less challenging to make them? Or is that just for fun?
Well, it is a little bit of both, I'll have to admit. The main reason is because this project was on an accelerated schedule. We were trying to develop something that had never been made before, and that means going through multiple prototypes. Mm-hmm. And 3D printing allows you to go through multiple revisions of prototyping much easier than if I were to go to a machine shop and machine every single part and then realize, I need to, this radius needed to be a different diameter. Now I have to start all over and redo it.
Right.
Well, with the 3D printed robot, you can identify 10 different changes, just make them in the model, print it, and the next morning you have a new robot body.
Cool, yeah.
And so we're able to go through many different revisions of these robots. And from the time that we started, it took us about 2 years to get something where we were able to go in and inspect inside of a dry storage canister.
I mean, that's pretty quick for a robot that can go inside a dry storage canister.
Yeah, and withstand thousands of rads per hour and, 150, 200 degrees Fahrenheit temperatures, yeah.
So are you allowed to say what material it's made out of?
Well, yeah, we made them out of all kinds of different materials. So originally we printed them out of ABS plastic. Okay. It's kind of it's a balance of high temperature resistance with high radiation resistance. It's relatively good at both, but maybe not perfect at either one. We actually experimented some with tungsten infused plastics because tungsten works as a very good radiation shield. Originally, we thought, hey, this is great because, we can protect our electronics, and then we realized later that the electronics didn't need as much protecting as we thought.
Interesting.
And the tungsten-infused plastic was both very expensive, very heavy, and somewhat brittle. So we've moved on since then.
You don't want your robot that's checking for cracks to be cracking.
Exactly.
It's going to mess up the reading.
Yep, so we've been able to do that, and one of the really nice things about the 3D printed robots is you can actually print in and have maybe a 2-part body where you can have all the electronics that are integrated into the body of the robot. Mm-hmm. And so you just print it in, and then everything is protected, shielded, so we don't have what's called FME or foreign material exclusion problems where you cut a wire or lose a bolt or something pops off because it's all integrated inside of the body.
So how is the robot, this might be a little bit out of your expertise, but I guess you helped make the robot. So
we've been working with a company out of Tennessee called Robotic Technologies of Tennessee. Fantastic small outfit. They can make wonders happen. So basically what we do is we sit down and say, these are all the things I want it to do, and then they make it do it.
Got it.
It's fantastic.
Yeah. It's so how do you transfer the data? Like, don't you usually transfer data through a wire that's connected to your computer? And so obviously you're not going to put a wire in the spent fuel.
Yeah, so what we do, we don't actually go inside of the canister, so maybe I misspoke a little bit. There's an overpack, so we go inside in the annulus space between the canister and the overpack.
Got it.
So that's that narrow gap that I was talking about. And what we do, because it's a nuclear application, we have tethers on them. So if anything were to go wrong, we can pull back and pull the robot out if it loses power or gets stuck or anything else were to happen. So we have 2 500-pound pull cables that are integrated inside of the communications cable that provides power and also transfers the data back, whether it's any kind of NDE technique.
So how big is this robot?
Well, we have several different ones. The smallest one is about the size of 2 cell phones stacked on top of each other, 2 of the large cell phones. Small. So very small. Some of the other ones are maybe about 6 by 10 inches, so a little bit bigger. And then we have 2 or 3 that are about like that. And then one of them that I really like, it might be my favorite, is we have a multi-stage robot. Some people call it a marsupial robot because it's like one deploys another, or I call it like a mothership and deploys the daughter ship, if you will. But it's a multi-stage robot where one robot goes in and then deploys and reaches up and deploys the second robot.
That's pretty cool.
It's so cool.
And how big is that one?
The bigger robot is pretty large. It's about 4 feet wide, about a foot long, and a couple inches tall.
Okay, yeah, that's what I was imagining, because you're saying these are like 16 feet high. Did I get that right?
Yeah.
Yeah. So for, 2 cell phones to basically go around that canister, I feel like that would take a while.
Yeah, so typically we have kind of two different modes of transportation inside the canister. So a lot of the overpacks have a carbon steel liner, so that's magnetic. So we put magnetic wheels on the robot, and then they just stick to that and drive anywhere they want. Some of them don't have the carbon steel, so we can't get away with cheap, easy, simple magnetic wheels, and we use a vacuum suction system. So then the trick is, so if you think of inspecting a cup, we have a lid on the top. Well, we have to inspect the lid and the side, which means you have to go over a 90-degree bend.
Right.
So we have some again, the robotics company is very good. So they've developed a specific transmission where they can go over those 90-degree bends with either magnetic wheeled robots or vacuum suction robots. So it maintains a seal while it goes over a 90-degree bend, which you almost have to see in person to really believe that it's possible, because you're thinking, how can you do that with, you have to move the vacuum as the robot moves and adapt the vacuum so that you don't lose seal as you're going over this 90-degree bend.
Yeah.
So
are there videos?
There are videos.
I'll have to look them up.
Yeah, so we have them in some of our EPRI reports that we've developed that are freely available to the public. So if I remember the numbers right, we have a wonderful numbering system at EPRI. So the first report is 3,002,008,234. That's some of the
That's the
initial
number
work.
of the report?
And there were like 8 zeros in front of the first 3 billion. So it'll take us at least 2 or 3 years before we get, fill up the entire numbering scheme.
Yeah.
We did another report that isn't just EPRI work, but kind of the global industry. What is everyone doing to work on this problem of inspecting dry storage canisters? It's been a big issue. I wouldn't say a problem. It's been a big issue of concern in California. The public there is very concerned about, we're shutting down nuclear plants. The nuclear waste has nowhere to go. What's being done to make sure that the canisters are safe? And so that's been a big drive of why we've been doing the project. So we also put this other report together. That's 3,002,010,617 that describes all the work that, some 20 plus organizations are doing around the world. And then we did a follow-up of what is EPRI doing, and that's 3,002,010,621. So that's kind of a follow-up to the first report. And that last report, the 10,621, has videos embedded in the report. So anyone can go and download it for free, scroll through and watch the videos of the robots in action.
Amazing.
Yeah.
That report sounds extremely extensive. From the work that you personally have done with inspecting the dry storage caskets, and I guess your knowledge of that report and some of the other work that EPRI does, do you feel like dry storage is a problem that needs to be solved?
No, really, it's kind of an ingenuitive solution to a problem that came up with not having anywhere to put the used fuel. So, as you know, probably better than most anyone, Yucca Mountain was our repository in the U.S. that the license submittal went in, and then due to political issues instead of technical issues, which we would hope it would be technical issues that would stop things, not political issues. Yucca Mountain is going nowhere. And it's not unique to the U.S. I mean, there's really only a couple of countries around the world that are making progress, and it's because they were able to remove or ameliorate a lot of the political issues.
And do you have hope for our political issues and maybe getting Yucca Mountain up and running one day?
Well, I try and stay out of the political side. We're a independent, unbiased third-party nonprofit, so we don't get into politics. All we do is try and solve technical issues.
Yeah. And I saw that you are working on wet storage as well.
Yes.
So what's wet storage, and should we go in that direction?
So wet storage it's typically what comes before dry storage. So once you've operated the fuel for 4 to 6 years in the reactor, squeezed out as much energy as you can out of it, then it goes into a spent fuel pool. And it typically stays there for anywhere from 5 to 30 years while the radionuclides decay away and the fuel gets cooler. And once it gets to below a certain threshold, then you can load it into dry storage. So it's kind of the life cycle of the fuel from you mine the uranium, you enrich the fuel, you make your fuel, you operate it for 4 to 6 years, get the energy out of it, then it goes in the spent fuel pool, then dry storage, and someday transportation and disposal.
Someday.
So in the wet storage world, there are a lot of other things that we need to be aware of and respond to. So some of the things that we're doing at EPRI is because of, again, the issues on the far back end of disposal, spent fuel pools originally were designed to where you just put the spent fuel in and you space it out for criticality and you just left it there to cool off while the repository is being built, and then you would just send your fuel away and life would be wonderful. Mm-hmm. But because of delays in Yucca Mountain, not only in the US for Yucca Mountain, but other countries around the world, they needed to redesign the spent fuel pools and put the fuel closer together. And to be able to do that, they had to put neutron absorbers in between to prevent criticality in the spent fuel pool. Criticality is where you're...
Oh, go ahead.
That's where you're generating power from fission. So you want to do that in the reactor. You don't want to do it anywhere else.
Yeah. Why did you have to move them closer?
The spent fuel pools were running out of space. So you had... The only way to safely move them closer together was to put neutron absorbers in. And so recently there have been some concerns over how are these neutron absorbers performing. Many had been in service for 20, 30 plus years, and they had originally coupon programs. Mm-hmm. And so they would take a coupon out every few years, typically every 4 years or so, and look at it, they would dry it, do some tests on it, and then throw it away. Well, after a while, you run out of coupons. You only have so many. And so some of the work that EPRI was doing was evaluating, okay, a lot of these plants are getting towards the end of the coupons. Are we still in a safe condition? Do we need to re-rack spent fuel pools? Because you can take out the neutron absorbing panels and replace them with new ones. But to replace all the panels in a single spent fuel pool is $20 to $30 million. So
wow.
It's a very large expense that may not be necessary. And if you multiply that around the world, if every spent fuel pool of every reactor had to be replaced, you're talking 400 times $25 million. What is that, about $10 billion? Somewhere in that range. So that's a big expense.
For like one site?
That would be worldwide.
Worldwide.
For one site, it'd be about 25 million. And so what EPRI did was set up what's called the Industry-Wide Learning Aging Management Program, or ILAMP. We're getting better with acronyms now. So the ILAMP program is meant to take data from plants around the world, not just a single plant, how we did it in the past, but combine the materials, the neutron absorber material, whether it's a boral material, a carborundum, a metamic, or various other neutron absorbing materials, combine that with the spent fuel pool water chemistry data that's being collected, and combine those into a database where we can look for trends, where we can rely on each other. So if my plant has run out of coupons, but you have a plant that operates similarly with the same material, same water chemistry, everything else the same, we could potentially call them sister plants and then rely on each other. So that if my inspection finds anything, I can notify you. If your coupon examination identifies anything, you can notify me. But if we both find nothing, instead of each of us having one data point, now we have two. And so we can combine these around the world to where now instead of every plant doing it individually, we work together and we can better identify trends, we can better get in front of any issues that may be coming, as well as if there aren't any issues, we can also say, okay, we can change how we operate to be more efficient. So it really comes down to, what does the data tell us?
Yeah, that's fascinating. And you guys are in the stage right now where you're gathering the data to see if this system could work?
Yes, so it's been preliminarily approved to go forward. So we're setting up the program. We've been doing that for the last year. We've gathered about 100,000 data points from water chemistry, and we're setting up and gathering as many neutron absorber coupon data points as we can as well. And so sometime next year we'll be publishing that and then really setting up to allow the utilities to provide the data to EPRI to then go into this database that then all the utilities can draw from and learn from.
Yeah. And for your preliminary, I guess you would say, model, what sites are you looking at? Are they all close together already, or are they pretty dispersed?
Well, it looks like almost every utility around the world uses what's called the EPRI water chemistry guidelines, where we have limits for chlorides, sulfates, and fluorides, which are the main corrosion accelerants that we would have in water chemistries. And what the water chemistry guidelines say is that all three of those have to be below 150 parts per billion, which is very low.
Very small.
Yeah, so they typically keep their water very clean.
Yeah.
But what that helps to do is minimize or essentially eliminate corrosion in the spent fuel pool. So it means that not only is your fuel not corroding, but your neutron absorbers typically aren't corroding either. So now that said, there was one material that really is kind of out of favor and not used anymore that was called Boraflex, that was used back in the 80s and maybe early 90s, that did have some issues with corrosion. So it's been replaced at almost every utility, and the ones that still have it don't take credit for it. In other words, they act as if it's not there, even though it is there and absorbing neutrons.
Can you say that again?
So nuclear plants are very conservative.
Okay.
So a lot of times they'll do something that makes the situation better, but they don't take credit for actually doing that, which sounds kind of silly. You know, if I buy a car that has side impact airbags, the car manufacturer is going to let me know because they want to charge me more for that.
Yeah.
Well, nuclear plants are a little bit different. They do all kinds of things in the name of safety, but a lot of times they just do it as an added buffer or an added cushion to safety. So when it comes to some of these neutron absorbers, once plants identified that, hey, this one particular material is corroding away or having not providing 100% of the effectiveness that we had hoped for, they take zero credit for it. They act as if it's not there.
But they keep it.
Even though it is. And then what they do is they'll spread out their fuel or do what's called a checkerboard, where you essentially have every other fuel assembly is empty. So plants do things like this to maintain significant margins to safety.
How would you balance maintaining that margin of safety, though, with maintaining operating costs and maintenance costs? Because that sounds like a lot of maintenance, and as we were just talking about, it can be really expensive to change the storage.
Yes, so there are a couple of things that we're doing right now to address that. One is we're looking at reactivity depletion uncertainty calculations, which I'm sure everyone on your podcast is very well aware of.
Oh yeah, does it have an acronym? I'm sure you could just use the acronym for.
No, so reactivity depletion essentially means that as the fuel is burned up, as we squeeze the energy out, it has less ability to produce more energy. It's kind of like if you burn a log, it has less ability to continue burning the more you burn it. So the fuel is like that in a sense that the more energy we extract out of it, the less reactive it becomes. And so EPRI has developed what are called the EPRI benchmarks, which are looking at what is the uncertainty of that depletion. And so in the past, typically utilities, based on an old memo from a long time ago, and some engineering analysis and judgment, said that 5% was a good uncertainty number to use. And what we found through a multi-year study is that really if we take into account actual conditions versus assumed conditions, that those numbers are actually more like 1.8 to 2.5%. And it may not sound like a big difference to go from 5 to 3 or 2.5%, but it actually is in a criticality space. So it provides a lot of margin to get those extra 2% and a lot of operational flexibility. And so one of the things that EPRI's been doing is working with our regulator here in the US as well as regulators around the world to get acceptance of using these more accurate reactivity depletion uncertainty numbers. You could have a whole podcast on that.
Oh,
I'm certainly not the expert.
We'll have you back on, and everybody that you work with back on to talk about it more, because this is an area that doesn't get talked about a lot because people just don't like to talk about it.
Yeah, so what we're looking at now is typically going from 5 to 3%. So still maintaining margin to what the real numbers are, down at around 2%. But going with, these 3% numbers allows the plants to be more efficient in how they operate their plants, which a lot of times efficiency also leads to safety. Because if I have to unnecessarily move a fuel assembly because of an imaginary issue, I'm doing an at-risk item that I didn't need to do. So I'm getting people real radiation dose, having a fuel move, which is a real risk, albeit low, but a real risk for an imaginary issue. So it's kind of like with, I joke about analogous issues that may happen in other areas. Maybe joking is the wrong word, but when it comes to the climate, because of the way we're operating our power plants right now, we're killing real people to save imaginary ones.
Yeah.
Like we're shutting down nuclear plants, which save emissions, save lives for imaginary people saving. So we're killing real people in other countries, around the world that are operating lots of plants that have significant emissions to save imaginary people. So in this case, it's very similar that we're creating real risks to prevent imagined risks.
Yeah, I'm so glad you said that, because I feel that all the time, and it's really hard for people to accept any risk. And in them trying not to accept any risk, they create these risks that they don't really think about. And I think it's all about perception, right? It's like, oh, well, I don't want the risk of, like, say on a large scale, like I don't want the risk of nuclear power plants being in operation because something could go wrong, but I can't see the risk of operating plants that have dirty emissions right now. So I'm inherently accepting that risk, but I don't realize it because I think that I'm accepting zero risk by saying no to nuclear.
Yeah, and the stat that always was interesting to me is that years ago when nuclear was very out of favor with environmentalists, that your average coal plant would actually put out 100 times as much radiation as your average nuclear plant.
Interesting.
Now that's gotten a lot better today with improvements to emission standards, so maybe it's more like a 3-to-1, but there's still actually more radiation that comes out of a coal plant than a nuclear plant.
Actually, I never knew that.
Yeah.
So thanks for informing me on that front.
Now they're both very low. I don't want to scare anyone. I mean, they're both very, very low. I mean, on the order of, sleeping in bed next to someone, radiation dose low. You actually get radiation dose. We're giving each other a very small amount just talking to each other today.
Yeah.
But it's so small that it doesn't matter. It's not ever going to give one of us cancer.
Right.
But it's one of those things where just because we can measure a very small number, it can still scare people that, I'm getting a tenth of a nanosievert. What does that mean? All radiation in some people's mind is bad.
Yeah.
So
it's interesting. In other people's minds, a little bit of radiation all the time is good.
Yes.
So, or in some people's work, I guess, not even just in their minds. But.
Some studies have shown that there may be a benefit to radiation. So I'm not an expert in that area. I look forward to seeing where that research goes.
Yeah. And so one thing that interests me is that I think that there's a lot of people in positions similar to you in the nuclear field that don't have the same opinions about risk or about increasing, or I guess reducing the margins so that we can operate plants more efficiently, even though you have to sort of make the more difficult decision to say, like, hey, we don't need to be over safe and have extra safety systems. So what was it that you saw in the industry, or maybe you experienced or you read, that sort of led to that conclusion in your mind of, like, these systems, safety systems, are extra?
Well, I generally don't make the judgment call of what safety systems are extra. That's typically up to the plants. Now, one of the things that we are doing at EPRI to understand what the margins are, because that is something we do. We try and understand what are the real risks? What does the data show to us? One of the large-scale tests we're doing right now is what's called the high burnup demonstration project. So we're trying to understand what are the real risks for storing used fuel in dry storage. So there have been all kinds of opinions that have been thrown out about, used fuel will be perfect forever in dry storage, or used fuel begins to fall apart the day you put it in dry storage, and everything in between the two. So one of the things EPRI is trying to do is, again, not take sides, not make opinions, but present facts.
Right.
So with what we're calling the high burnup demonstration program, or we call it affectionately the demo, it's a long-term, large-scale collaboration between the Department of Energy, EPRI, the U.S. National Labs, vendors, nuclear vendors, and Dominion, actually not too far from here in Virginia, have all teamed up together on this 15-year project to design, license, manufacture, load, and then monitor a dry storage canister with only high burnup fuel. So we in nuclear are terrible at naming things. Instead of calling it high efficiency fuel, which is really what it is, we decided to be nuclear, engineers first, and nuclear engineers even worse. We call that high burnup fuel just to scare everyone,
right.
Apparently. Now, technically, that is what it is. So there have been a lot of concerns that it's high burnup fuel. It must be bad. It must be dangerous. And one of the things, why I think we should have called it high efficiency fuel is we're using more advanced alloys, better materials, like we talked about earlier. So these materials respond better. We're using advanced concepts in how we operate the plants so that we have less degradation that can happen to the fuel, less corrosion. And then we're basically treating the fuel better. We have more advanced alloys, and we're sucking more energy out of the fuel. So really, all of these things are good things, but they're perceived as bad because of a bad name.
Yeah. What does burnup mean?
Burnup is essentially how much energy you've extracted from the fuel.
Okay, so basically high burnup, are you trying to communicate you extract more energy from the fuel?
Yeah, so burnup is expressed in either megawatt or gigawatt days per metric ton. So it's this weird acronym that you see, like GWD over MTU, and you're like, what the heck? It's gigawatt days per metric ton uranium. So it's essentially how much energy did we extract from the fuel. And so the more energy you've extracted from the fuel, the less energy that remains.
Right.
Now that said, the higher burnup fuel will have, it'll have undergone more fission, which creates more fission byproducts or more byproducts of the fuel. So it'll typically have higher radiation and more decay heat than low burnup fuel. But some of the benefits that we also get, and there was actually a recent EPRI report, and I'll stop spouting the 3 billion, 2 million numbers to you. But there was a recent EPRI report that talked about the bonding that actually happens between the fuel pellets and the cladding, which creates a composite material where each of the materials interacts with one another and creates essentially a better overall material and a safer material. But that said, again, we wanted a demonstration program. So it's not just, we have this study over here and this study over there, and then making tenuous connections between them. So with this co-funded project between EPRI and the Department of Energy, we loaded 32 high burnup fuel assemblies into a cask. And the really interesting thing about this cask is that they inserted thermocouple lances in various areas. So there were 63 different thermocouples that were inserted. So there were 7 different thermocouple lances with 9 thermocouples each, so we can get different heights and orientations of temperatures. And so that cask is sitting out at North Anna right now, just sitting there collecting data that's being used to understand what are the temperatures, what are the environments the fuel is being exposed to. Is there some sort of degradation mechanism that's happening? And really what we're seeing so far, and I guess it's a matter of opinion there, is really a lot of boring data. It's just sitting there
good.
doing nothing. Yeah. So that the opinion is, okay, yeah, that could be good. So the end goal of that project is after 10 years to open it back up and examine the fuel.
Why 10 years? That seems like a really long time.
It is. So it's really a balance of, we want to understand what happens over a long period of time, because if there is a degradation mechanism that happens slowly, that may take years, months or years to develop, we want to make sure that we didn't stop it too soon. So that anything that could happen has a chance to happen. So one of the things that has been a big concern of many people for a long time is what's called hydride reorientation. So as the fuel's in the reactor, the water comes by, fission happens, and the fuel rods will pick up hydrogen from the water. And typically it's a very small amount, but then when you go in the spent fuel pool to cool down for a certain period of time, then you'll dry to go into dry storage. And the drying process elevates the temperature. And there's a limit right now of 400 degrees Celsius. That's the limit in the United States and most countries around the world, to limit the effects of hydride reorientation. So what happens is the hydrogen will exist in the cladding, and it can diffuse and move because hydrogen is a very small atom. And what can happen is when you heat it up, a lot of the hydrides that are essentially almost like a composite material, a hydride material, a combination of zirconium and hydride, they're typically oriented circumferentially or around the fuel rod. When you heat it up, they can go into solution, and if the fuel rod is under stress and at a high temperature, when it cools back down, the hydrides will follow the stress patterns. So if it's under high stress, then they may orient radially. And if they orient radially, it could present a weaker path. It could weaken or embrittle the fuel. So it's one of the things that we're looking into. And part of the motivation here is we're trying to understand, what is the propensity for this to happen? Is it truly a bad thing? And so one of the benefits that we've gotten from this high burnup demonstration is the temperature data. And so what we've done with the temperature data is use it as a blind benchmark to our thermal models. And again,
it's coming back to the start.
Yeah, we talked earlier, there's a lot of different conservatisms that we build in. So, if my number is X, I assume it's 1.2 or 1.5 or 10X. And so in the thermal modeling that they do, there's a lot of these conservatisms that are built in the models. And so in modeling space or in theoretical space, a lot of times we think we're at or very near this 400 degrees C limit. What we did with this thermal model data, or the high burnup data, is we actually kept that secret for a long time. And we had several different organizations run their thermal models with the inputs of the fuel, and then compared them to the actual data. And what we found is that pretty much universally, the thermal models are significantly over-predicting temperatures by 25 to almost 100 degrees Celsius.
Wow.
Too high.
That's a huge difference.
Yeah, so it's kind of like if your weatherman predicts snow and it's boiling outside.
Right.
It's that big of a difference of the temperatures. So if you can imagine, we have these potentially very high errors where certain degradation mechanisms can happen if we get very high in temperature. And so if we're much lower than we thought we were,
right,
that's actually a very good thing, because certain degradation mechanisms like this hydride reorientation can't happen, or can only happen in a very, very limited fashion to where it would be negligible and not an issue. So one of the things we're finding is with the high burnup demo, we didn't expect to get value for 10 years, but because of the way we're using the data, we're actually getting value now and finding out that, again, we're much safer than we originally thought we were.
Do you think that because the initial findings have been positive that you guys could say actually use the high burnup fuel before the study is completely finished?
Well, I'm not sure if I understand.
Or at least use like the tweaks that you guys are making to the high burnup fuel, because you said this is a 15-year project, but your preliminary data suggests that it's more efficient to treat the fuel in the way that you guys are treating it now, which I presume isn't the way that it's being handled at most operating plants at the moment.
Yes, so that's a really good point. So we are looking at what are all the touch points of the high burnup demo and the thermal models all along the back end of the nuclear fuel cycle. And really what we're finding is that thermal controls everything. Mm-hmm. So in your spent fuel pool, as soon as your fuel comes out of the reactor, you have time to boil calculations. So you have to continually cool your spent fuel pool as if it's hotter than it really is. Mm-hmm. So that creates some operational redundancies, some additional constraints that maybe aren't needed. Next, if we can improve the accuracy of these thermal models, there's the ability to move fuel less. So again, reducing the risk by not needing to remove fuel as much. We can also load it into dry storage earlier, because if we have to wait for it to cool below a certain level, if we think it's hotter than it really is, we have to wait longer.
Right. And
there are actually safety benefits of moving out of the spent fuel pool and into dry storage. Now, both are very, very safe, extremely safe, in fact. But if we're going for the safest option, dry storage will be a little bit safer because it is a passive safety system. We don't have to actively cool it. Mm-hmm. It just sits outside or in a building and is consistently cooled by the environment. So we get all of these benefits. We find out that fuel is cooler than we thought it was. That means it will maintain its toughness or its ductility, so it's easier to transport. We can be more flexible with how we transport it. And really some of the biggest benefits that we can get from these more accurate thermal modeling efforts are on the very far end, the back end of the nuclear cycle. And we don't like to talk about it much, but all nuclear reactors will have to get decommissioned someday. Mm-hmm. And one of the big cost drivers for decommissioning is the spent fuel pool. So maintaining a spent fuel pool can cost $25 million per year or more. So if we can take off 1, 2, 3 years that we don't have to continue operating and maintaining a spent fuel pool, we can get a safety benefit from moving into dry storage earlier. We can also get a cost benefit of anywhere from 25 to 50, $100 million in the decommissioning space. So that's good on both sides. And the biggest benefit comes even after that, and that's in the repository. Because again, thermal controls everything. Mm-hmm. The limiting factor for a repository footprint is how much heat it can dissipate. So we can actually fit significantly larger amounts of spent fuel if we can pack it closer together, kind of like in the spent fuel pools. If we can pack it close together, we can get more in there. So with repositories, with improved thermal models, we believe we can get anywhere from 4 to 9 times as much fuel into a repository. So if you're talking a repository that costs $100 billion, and now we can fit 4 to 9 times as much fuel in there, we're talking hundreds of billions of dollars of savings just in the US.
Right.
And then multiply that around the world. I mean, we could potentially save $500 billion, $1 trillion because of the improved thermal models that all started from this high burnup demo.
Yeah. So what are some of the next steps that we need to really get there? Because we're pretty far off from that right now.
Yeah, well, we might be closer than we think, but you're right.
Good.
We're not there yet.
It.
We are definitely not there yet. So one of the things that we're working on right now, again with the DOE and various other organizations, is what's called a PIRT, a P-I-R-T, a Phenomena Identification and Ranking Table. So it's looking at what are the influential factors, what are the gaps that we have in our knowledge of these factors, and how influential are they? Mm-hmm. So if we have an item that we have a low certainty of and has a high sensitivity, as in it can make a big difference, that's a big gap.
Mm-hmm.
Whereas if we have something that we understand very well and it has a low sensitivity, that's something we can say, okay, we know what we need to know here. We don't need to chase our tail. We don't need to get more data. So it allows us to help rank the different items where we need to go after, get more data to make these conclusions. So that PERT process is going on right now.
Mm-hmm.
There will be a report out sometime next year. So we're hoping to push that forward as quickly as we can because of all the safety, efficiency, and economic benefits across the board for the back end of used fuel and management.
Yeah, looking forward to it. You'll have to send it to me once it comes out. In particular, with the spent fuel to begin with, why don't we just say add it to some sand or some soil or gravel, mix it all up, and just spread it on, say, farms or other land?
That's a good question. Maybe not too hard. One of the reasons why we spend so much time working on, doing R&D on, and managing used fuel is because it's one of those things we don't want to pass on to our kids and grandkids, the burden of, we got the energy, now you deal with the waste. So when it comes down to used fuel, it is very highly radioactive. So if we grind it up and spread it out, there would have to be a significant dilution. I mean, a very large area to dilute it enough. Now, that said, if we have repositories or other solutions like this, we can put it in a place where it can be maintained in a safe state for hundreds of thousands or millions of years. I mean, some of the geologic formations that have been discussed for housing used fuel can be stable for many millions of years. So by the time that anyone would be exposed to any byproducts, or even if there were drilling operations that we forgot about it a million years from now, that the used fuel would have decayed away to the radiation levels being background uranium levels. So it's one of those things where it's really a part of being good stewards of our planet to maintain, and it's really all across. It's not just nuclear waste, but other forms of energy have waste that they also have to deal with. We have coal ash that our counterparts, our brothers and sisters over on the coal side, they have to work with and deal with. And so what we try and do is also learn from each other. So some of the things that we're doing can benefit them. Some of the things they're doing can benefit us. So we really look at it as we're working together to manage the waste products that come out of our energy cycle. And there's no perfect energy source. As much as we all love renewable, clean energy, we also have to remember that even solar panels have toxic materials in them. Mm-hmm. Wind turbines have vast, 20, 30 years from now, when we start tearing down wind turbines, we're going to have a large stockpile of wind turbine blades that we'll also have to do something with. So we're not unique in nuclear that we have to deal with our waste. All forms of energy have to deal with it somehow, and we can all learn from each other.
Yeah, absolutely. And in your answer, it kind of sounded like a hint of your vision of energy for the future would include in large part nuclear, but I guess just directly, what is your vision for the future of nuclear energy?
Well, my vision for the future of nuclear is to play nice with other forms of energy. Sometimes we kind of get up in our heads and have a big head about nuclear that, it's safe, it's the safest form of energy, it's clean, it's this, it's that. One of the things we need to do is realize that people want a choice of the energy that they have. Mm. Some people want solar, some people want wind, other people love hydro. So we need to operate our plants in a way that we can be complementary to these other forms of energy, including even energy storage. So if we can have clean forms of energy that play nice together, that provide safe, affordable, reliable, and environmentally responsible energy. That's kind of EPRI's mantra: safe, affordable, reliable, and environmentally responsible. But also in a way that's resilient and flexible so that it can adapt to our future needs. That's my vision of the future.
Yeah. Jeremy Renshaw, thank you so much.
Thank you.